Okay, so I want to start screencasting the solutions to the mock exam, exam 3, in preparation for the final examination next week. If we look at question 1, this is going to be a very typical question for the first 5 questions on your final. That is, you're going to be given a structure and you need to identify the proper IUPAC name. So if we go to the structure, I want to count the longest chain. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. So that has a nonane root. Now it's not going to end up being nonane because I'm going to have a double bond and a triple bond, and of course an alcohol to account for. So how about non-an 7-ene 4-ine 2-ol. And then we just need to account for the stereochemistry. So we know that the hydroxyl will be priority 1. This carbon's priority 2 because it's bonded to the triple bond. And of course this is priority 3. The H is already oriented away from us, so we simply need to go 1 to 2 to 3. That's clockwise, so this is going to be R. So as we look at our answer choices, we want to eliminate C and D. And then finally we want to eliminate A. The best answer choice will be answer choice B. So number 1, the best answer is B. And you're going to have 5 questions like this on the final, so you might as well do enough of these to get really good at it, because these are 5 easy points if you put in the work. Now let's move on to question number 2. And we want to find the structure that corresponds to 2R, 3S, 4R, 5R, 2, 3, 4, 5, 6, penta, hydroxy, hexanal. And we have a lot of different Fisher projections. So really this is not a very difficult problem if you think logically and you just try to make the approach as easy as you can. So let's just look at the first chiral center, and we're going to do HOH. Of course, this is a mess of things. You're going to have other H and OHs here. I just want to assign priorities. The highest priority, of course, will be the alcohol, and the lowest will be the hydrogen. Number 2 priority will be the aldehyde, because it's making 2 bonds to oxygen. And number 3 priority with this other chain. Now 4 is not oriented away from us, so what I would do would be flip 2 labels twice. We can do 4 and 2 and 1 and 3. And as we go from 1 to 2 to 3, that is indeed R. So R occurs when the hydroxyl group is to the right. And S will occur when OH is to the left. Because the aldehyde carbon, or the carbon closer to the aldehyde carbon, will always have the higher priority over the carbon that's farther away. Hydrogen will always be the lowest priority. The OH will always be the highest priority. And so we can very quickly determine the proper structure should be as follows. On carbon 2, we want R, so we put OH to the left, or excuse me, to the right. On 3, we want S, we put it to the left. On 4, we want R again, OH to the right. And on 5, we want R, so again to the right. Now, if you recall, there was a typo on question 2. That structure is best represented by D. So D is the credited response for question number 2. In other words, the structure of 2R, 3S, 4R, 5R. So if we look at question number 3, we have 1, 2, 3, 4, 5, 6, 7, 8. So that's octan. And of course we have a diene. So we want a number from left to right to have the lowest number. We have 1, 2, 3, 4, 5, 6, 7, 8. That's octan 3, 5 diene. We need to look and see if structural isomers are in play. So on this side of the double bond, ethyl has the larger priority. And on this side, it is the fluorine that has the higher priority. Those are opposite, so this is an E double bond. And of course, I'll render this next one in orange. Higher priority, higher priority. These are Z because they're together, Zusammen. And so we will have 3E, 5Z. And then, of course, the fluoro is going to come first because F occurs in the alphabet before M in methyl. So we'll go 4 fluoro, 3 methyl, 3E, 5Z, octan, 3,5-diene. And that, my friends, is a mouthful. Of course, we had to change a couple of the answers on this one. So the best answer is going to be answer choice A. A is the credited response for number 3. Moving on to number 4. We are given a structure in the chair conformation. And we have an axial chlorine and an equatorial ethyl group. We draw an equator around the middle. We see both of these are going north. And so this is cis. Now when it comes down to an alkyl or a halide, the halide wins. Cis 1 chloro 2 ethyl cyclohexane. cis 1-chloro 2-ethyl cyclohexane. That is going to be answer choice B. So number 4, the credited response is B. So if we look at number 5, we're given a structure of biotin. Biotins are important in mediating 1-carbon transfer reactions in mammalian systems. Let's start with the obvious functional groups. We have a carboxylic acid. This one's a little bit controversial, but we can call this a cycloalkane. It just has a sulfur in it. You have an amide. You also have a carbon-sulfur-carbon bond. That's better known as a thioether. Remember, thio means sulfur. So the answer that best sums up these functional groups is answer choice D. So D is the credited response for number 5. Number 6, real interesting question. It's a real popular one on the final exam. Hint, hint, cough, cough. If we have a formula of C5H10O2, functional groups that have 2 oxygens. Carboxylic acids have 2 oxygens. Esters have 2 oxygens. Alcohols, not necessarily. Ethers really don't have to have 2. They can get by with 1. And acid anhydride, that's 2 carboxylic acids that have been condensed, so you lose water. And so the most simple acid anhydride has 3 oxygens. That means the best answer is going to be D, the ester. So number 6, the credited response is an ester. And let's fit number 7 onto this particular slide. We're looking for the bond angles in AlCl3. Remember that aluminum is trigonal planar. And by trigonal planar, it has a lobe of an empty p orbital that comes directly out of the screen towards us. And we have a p lobe that goes into the plane of the screen directly away from us. So there's no lone pairs to depress bond angles. Essentially, you have an equilateral triangle, if you will. These bond angles are 120 degrees. So for number 7, the credited response is answer choice C. So number 8, we have formal charge in boron, NaBH4, and also the formal charge in aluminum in LiAlH4. Remember, these are both used to reduce aldehydes and ketones to alcohols. In boron, you have a tetrahedral complex where boron is making 4 single bonds to 4 different hydrogen atoms. Boron has 3 valence electrons. There are 4 atoms bonded to it. And so the formal charge will be -1. You could rationalize this with ODEC. So if we have 2s and 2p, after we get, so let me put the ground state first. With hybridization, we can promote this electron. In order for boron to make another bond, hydride with both of its electrons will overlap. And so one of these is being shared with the boron. Of course, the hydrogen brings a single electron with everything else. And so it has to have one more electron than normal, which is going to give it a -1 charge. Now, aluminum is in the same group as boron, should have exactly the same chemical behavior. Each of these group 3A elements will have a formal charge of -1. That's how they're so nucleophilic. The driving force is to break one of these bonds and for H and its electrons to act as a nucleophile. So number 9, the credited response, number 8, the credited response is A. Number 9, which is the most polar? We have a thioether. We have butane. We have water. And we have CF4. CF4 is absolutely nonpolar. The thioether and the alkane have very negligible polarity, but water is a bent molecule. In fact, if you charge a glass rod such that you've deprived it of electrons, it will attract the water towards it. So if you have a faucet and you have water dripping like this, and you bring a rod close to it, the water will respond by curving itself, not this way. The water will curve itself away from the rod. Water is a bent molecule. So for number 9, the credited response is C. And let's wrap this screencast up with number 10. We want to find the most thermodynamically stable radical intermediate, and you really need to proceed carefully here because you have the offsetting fact of the carbon-carbon double bond and the radical. First of all, this is not stabilized by resonance at all. We can quickly get rid of B. Both of these are allylic. Actually, all 3 of these are allylic. Tertiary, secondary, primary. However, this double bond only has 1 alkyl group. This double bond has 2 alkyl groups, but this double bond has 3 alkyl groups. The alkene is the greatest contributor to stability. Therefore, for number 10, the credited response is D. Got to look at the stability of the carbon-carbon double bond in addition to the stability of the radical. I'm going to stop this screencast. I'll pick up on number 11 for the very next one, and I will do as many of these as I can over the course of the weekend.